We are back. So now we're going to incorporate the concept of intermolecular forces with functional groups. And we're going to see what happens to the corresponding melting points, the boiling points, when we look at organic molecules within that frame of mind of functional groups. So just to remind you, you have four forces to be aware of. Probably the first three are the most important. London dispersion forces, dipole-dipole forces, hydrogen bonding. London dispersion being the forces that are only bound and found in molecules that contain nonpolar bonds. Molecules like alkanes, alkenes, alkynes that only have carbon-carbon and carbon-hydrogen bonds will contain simply London dispersion forces and nothing more. Other molecules that contain electronegative elements like the halogens or oxygen, nitrogen, in combination with carbon will create dipole moments that will not be cancelled out. If that's the case, the dipoles don't cancel out within molecules that have polar bonds, your entire molecule will end up being polar and you'll end up with dipole-dipole forces. And for those molecules that do contain nitrogen hydrogen axial covalent bonds or oxygen hydrogen covalent bonds or fluorine hydrogen covalent bonds, you will have hydrogen bonding additionally. Later down in the course, we'll talk about ion dipole forces for some of the molecules that will involve metals. But for now, the first three, London dispersion, dipole-dipole, and hydrogen bonding will suffice. So let's take a look at the functional groups and let's try to assess what they have in terms of molecular forces. And we're going to look at this from the point of view of molecular weights being roughly the same. So roughly the same number of carbons or the same number of second row elements within a molecule or family of molecules. And the first thing, as I mentioned, is that the alkynes, the alkenes, the alkanes, and even your regular aromatic groups only contain carbon-carbon bonds and carbon-hydrogen bonds. And it doesn't really matter that they are double bonds, triple bonds, or single bonds. The fact is that the electronegativity differences are not high enough in difference to create polar bonds of any kind. So these four groups automatically contain only London dispersion forces. But when we look at the molecules containing carbonyls like the ketone, the aldehyde, and the ester, the presence of that carbonyl creates a polar bond, a rather good polar bond that doesn't cancel out because you don't have another carbonyl bond going in the opposite direction. So you get yourself a polar bond. And you may ask, well, what about the other carbonyls? Well, what about to address them? They kind of fall in a different family because of an additional factor that they have within them. But ketones, aldehydes, esters, they just have carbon-oxygen bonds, carbon-carbon bonds, or carbon-hydrogen bonds. And that's the extent of it. So it's just the presence of that carbonyl, or in the case of esters, the presence of that extra carbon-oxygen single bond that creates a polar bond and gives you molecules with dipole-dipole forces. All right, now the carboxylic acids, the alcohols, the amines, and the amides, as long as you have NH bonds present, you don't have just dipole-dipole forces. You have hydrogen bonding as well, just because the hydrogen is bound to an oxygen or bound to nitrogen. And needless to say, if you have an amine that doesn't have nitrogen-hydrogen bonds, then, well, of course, in that case, you don't have hydrogen bonding. But here we'll assume that NH bonds are present, right? So the amide and the amine both have hydrogen bonding, same thing as the alcohol and the carboxylic acid. So we're kind of beginning to see a little trend right here. In particular, if you rearrange these organic molecules, this family of organic molecules, in terms of what you would expect for their intermolecular forces, well, you would say the first four, the alkenes, alkanes, alkynes, your aromatic molecules will have London dispersion forces. They will be the weakest one in terms of intermolecular forces, as long as you're comparing same number of carbons within group to group. So we would expect the boiling points for these molecules to be the lowest. And then the ones that contain the dipole-dipole forces, like your ketone, aldehydes, your esters, and of course, your ethers, imines, and nitriles, These ones will be intermediate, and the ones that do contain hydrogen bonding, you would expect to have the highest intermolecular forces, which, by the way, even within the diagrams, I'm kind of dividing it as such. The ones that have carbonyls, I predict to have higher intermolecular forces because you have that stronger dipole moment present as a result of the carbonyl being there. So this is roughly what we expect. We expect to see, your ketones, aldehydes, esters having lower intermolecular forces than your alcohols or amines, which themselves will have lower intermolecular forces than the carboxylic acids and the amides. And so this is kind of what we expect to see. Now, it's time that we do take a look at some experimental parameters, some experimental data, and see if our prediction solely on intermolecular forces, makes sense or not. And if not, we'll try to come up with explanations as to why we are seeing discrepancies. All right, so let's start with the melting points. What you see right here is a plot of melting points versus the number of carbons or the number of second row elements that your functional group possesses. So here for the alkanes, we have one carbon present. So this is, your CH4 fragment, and 2 carbons, 3 carbons, 4 carbons, 5, 6, etc., etc. And the same thing for the rest of the families, the carboxylic acids, the nitriles, the alcohols. And you can see by color scheme, what's kind of happening. And what you may already kind of see is that it's kind of messy. By the time you get to maybe 6 carbons, you see more of a linear trend to some degree, but even then, it's not a clean trend. And especially here on the left side, it's even worse, right? Because you start for the carboxylic acids kind of high, then they drop down. Your nitriles start kind of high, but then they drop down all the way here. By the time they get to 4 carbons, they kind of reach a minimum, and then they start going up. And so you have a little bit of a weird scenario. There isn't really like super clear trends. To some degree, you can maybe in this regime have a little bit of a linear trend where you say, okay, if you increase the number of carbons because you're increasing the molecular weight, you're going to increase the melting point, but it's not always true. And the reason that happens, and here you can see even more clearly, looking at the alkynes, alkenes, and the alkanes, you start at a certain value, and this is true for all of them, and then you drop down in the melting point. And then once you reach that minimum, you start going up again, but not in a linear way, because look at this. You go up, then you drop down again. Then you go up, then you kind of stay constant, then you go up again. And the alkene kind of has perhaps the best linear trend, right? The alkane is kind of bad as well. And this kind of is observed throughout the entire set of families, the aldehydes, the esters, the ketones, the alcohols. It means you have that higher point, then you drop down to some value, then you kind of go up again, and sometimes as you're going up, you have a little bit of like up and downs within that you know overall increase. So melting points are not necessarily linearly correlated to intermolecular forces. And you may ask at this point, like, well, what the heck? Like, what is the point of, even like addressing the intermolecular forces if we're going to have like almost no good trend for the entire family? Like, and you might even go as far as saying it's like intermolecular forces is shenanigans. It means nothing. Like this data is showing us that there is no trend. So this idea is not good. And that would be one way to go about it. But there's always, and this should be something you keep in mind as a scientist or future scientist, is that perhaps it's not that your theory is wrong, but perhaps there is a factor that you haven't included in your theory that because you're missing it is, messing up your entire predictions based on the observations. And in the case of melting points, the problem is that you are comparing apples to oranges. It's not a fair comparison. And the reason why is because when it comes down to solids, solids can um, be brought together. The molecules can be brought together into unit cells of various classes. Even within the cubic class, you have the primitive cubic, the barycenter cubic, and the face center cubic structures, which are all different. And by the fact that they have different number of atoms, they also change the overall density of the material, the overall volume of the material. So it's not an exact comparison. So you could have a longer distance between the molecules in a primitive cubic that you do in a face-centered cubic, and so the interactions are not exactly the same by comparison. And that's just in the cubic Rabe lattice structure. You could even be in the hexagonal structure, which is its own thing. You could be in the tetragonal structure. You could be in the orthorhombic, um, triclinic, monoclinic. So the point is that because you are not necessarily comparing the same overall unit cell from molecule to molecule, the comparisons of melting points are not necessarily linear. And that's what allows for those discrepancies. Now, if you were to compare only molecules that, let's say, crystallize in the body center tetragonal structure, in that case, you will see more of a linear trend as you increase the molecular weights. But because you are starting anywhere here, and we're not really telling you what the unit cell is for these molecules, you see all these discrepancies. And just to give you a clearer picture for organic molecules, right? Because the Barbet lattices that I'm being showing you are the ones for typical simple ionic solids. This ones right here um, contain actual molecules, and the molecules can actually be present within the unit cell, and they have their pattern, of crystallized structures, and you can use these patterns to ultimately elucidate the chemical structure of these molecules. So the actual solids, the solid materials of organic molecules can be very useful, right? But it is more complex. And look at this stuff. It's change the molecule somewhat, and you change the overall shape of how it's arranged. What unit cell is located in. So you kind of have to be careful. Now, that being said, melting points can be used for determining and assessing unknowns. If you have a molecule that is a solid, you could determine its melting point, and from that melting point you could potentially tell what the identity of the molecule is, or at the very least you could tell if your molecule is pure or not. And so I'm gonna walk you through some of the procedures that you perform with melting points. And right here I'm showing the melting point apparatus, the DigiMelt from SRS, and pretty much the techniques as follows. You have these capillary tubes right here, which one end is closed, the other one is open, and through the open end you kind of like tap into the solid right here. And then what you do is you invert the capillary. Either you tap it with your fingers, or the instrument might have a tapper function right here where you put the capillary and you kind of shake it until the solid drops down all the way to the closed end of the capillary. At that point you place the capillary in the melting point apparatus, and here with a magnifying glass you can actually see it melting as you increase the temperature. So this is pretty much the same idea, right? So you pick the sample through the open end, you invert it, and you tap it so that you get all the solid into the closed end of the capillary. You could use the tapper function if you have that in your melting point apparatus, and then you start measuring your samples, right? So that tapper function is kind of interesting. All right, so now let's take a look at the samples themselves. When you start with it, you have just the solids, right? And you start ramping up the heating within the melting point apparatus, and you start seeing the melting process taking place. So here is the onset, and as you go through it, you get to the phase where the solid finally kind of shows you a meniscus, right? So this is known as the meniscus phase. And after that, you can kind of still see some solid there. So it's almost like ice that's been in tap water, and it's not exactly, or even like a liquid that you have crystallized, that you have a frozen, that's kind of beginning to melt. That's kind of what this looks like. But then you get to the clear point where it's just the liquid. And traditionally, you report the range. You report the point where the onset begins to happen. That's the initial temperature. And you also report the point where the clear point finally appears. Now, if you were in the UK, you would actually record the onset and the meniscus as your range. But in the US, we go with the onset and the clear points. And typically for this type of instruments, you try to do this if you have the time, 1 degree Celsius per minute. That's the ramp time, or the rate for the temperature. So every minute the temperature will go up by 1 degree Celsius, and so on and so forth. Sometimes you could go a little bit faster, but the faster it goes, the less accurate your measurement is going to be. And the other thing too is that with melting points, you can assess the purity of your sample. In particular, we can exploit the colligative property of freezing point depression, because having even a 1% impurity can have a drop in the true melting point by about 0.5 degrees Celsius. So it's actually very decent. And if you have greater amount of impurities, you will decrease the melting point even more so. One aspect that I kind of need to tell you in regards to the future labs is that the melting point, as it drops, is going to drop below the melting point of both substances that are making up the solution, the solid solution that you're looking at. So if one solid melts at 100 degrees Celsius, the other one melts at 90 degrees Celsius, and you have a mixture of the two, the melting point of that mixture will have to be below 90 degrees Celsius. And we use that to determine the purity of the sample. Now, in the next video, we're going to talk about boiling points, and since the molecules themselves are not arranged in unit cells in the gas phase, we're going to see more of a clear picture of what's happening with them. Okay, so I'll see you in the next video.